All right, today we are going to talk about an introduction to sequences and series, kind of a new topic for most of us probably. A sequence is an ordered list of numbers. So any list of numbers that comes in a certain order can be defined as a sequence. A finite sequence is one that has a specific number of terms. So if it's a list of 38 numbers, it is a finite sequence. An infinite sequence has an infinite number of terms. It just keeps going forever. So there's some pattern to the numbers, whatever that might be, and it just keeps going on forever. That is an infinite sequence. So pretty simple. Finite if it has a specific number of terms, infinite if it goes on forever. But as long as it's an ordered list of numbers and there is some sort of rule for where those numbers come from, it is a sequence. We list the numbers into the terms in terms of which term they are. So there's a first term, second term, third term. We call that the domain, how many terms there are, or as the book puts it, the relative position of each term. And then the range, which are the terms themselves. So for example, a finite sequence would be 2, 4, 6, 8. There are 4 terms, and that's it. The domain is 1 through 4 because there are 4 terms. The range is 2, 4, 6, and 8 because those are the terms. An infinite sequence could be 2, 4, 6, 8, etc., meaning 2, 4, 6, 8, 10, 12, 14, 16, but it keeps going forever. The domain for that would be 1 to infinity. The range for that would be 2, 4, 6, 8, etc., etc., going on forever. So you can see that these are built on the same rule, but one is finite and one is infinite. We can describe the pattern for where the numbers come from with an equation, or what we usually refer to as a rule with sequences. So for this example, for these examples, I should say the finite sequence, a sub n, meaning the nth term of sequence A, can be found by multiplying the position of that number, or n, by 2. So if you look at the rule, you'll see how it works. For the first term, you plug in a 1. 2 times 1 is 2. For the second term, you plug in a 2. 2 times 2 is 4. For the third term, you plug in a 3. 2 times 3 is 6. For the fourth term, you plug in a 4. 2 times 4 is 8. That's how you find each of the terms of A for this sequence. And it can go on forever. You could write it as a rule like this, or as a function in function notation. They both work. So let's play with these a little bit. Describe the pattern, write the next term, and write a rule for the nth term. For the first one, we've got -1, -8, -27, and -64. So we need to think of a way to describe the pattern. So how are these numbers being constructed? So let me grab a marker. So I'm looking for any sort of pattern between these numbers, 1, 8, 27, 64. I'm wondering if they are cubes, right? So this could be 1 cubed, 2 cubed, 3 cubed, and 4 cubed. Do those work? Well, 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 is 16. Times 4 is 64. It works, but they're all negative. So we just need to make all of these guys negative. Right, inside the parentheses, and that's how we get our terms. So down here, you can write the terms as just like we just did. The next term would then be probably -5 cubed. -5 cubed is -125. And then a rule for that could be described as a sub n. This is how we write rules. A means the sequence, n means the nth term of that sequence. Is you take the negative number of the term and then cube it. So for the 1, 2, 3, 4th term, right? This is the 4th term. It's -4 because it's the 4th term, and then we cube it. So for let's say the 12th term, if we wanted to do the 12th term of that guy, it would be -12 cubed. And that's how we could find the next one. Okay, so now let's jump back and look at the second one here, B. 0, 2, 6, 12. So this is the first term, second term, third term, fourth term. Do you see a way that we can write a pattern or a rule that describes what's going on here? So take a second and see if you can come up with something. So they're suggesting we write the terms as 0 times 1, 1 times 2, 2 times 3, 3 times 4, So what do you think that next term would be? It's going to have to be 4 times 5, right? So the next one would be 5 times 6, and then 6 times 7. So the rule is going to be the number of the term, the nth term, times n minus 1. So if I want the 15th term, that's going to be 14 times 15, because the first term was 0 times 1. So we start with the first term. We have to go back one number to make 0. So then the second term is 2 times, go back one number. So you're always multiplying whatever term you're looking for by the number before it. So if I want the 15th term, it's 15 times 14, which would be 210, I do believe. Describe a pattern, write the next term, graph the first 5 terms, and write a rule. So go ahead, this is a yo-yo. Pause the video, take 2 or 3 minutes, and try to complete those 3 steps. Describe the pattern, you can just do that in words. Write down the next term. Graph the first 5, you can just sketch a quick graph, it doesn't have to be perfect. And then write a rule for the nth term. So pause the video and then come back. Okay, so here we go. We're going to describe the pattern first. Let's number these steps. So 1, describe the pattern. It looks like it's going up by 2. Starting at 3, going up by 2. So I'd say that's done. 2, write the next term. So that means the next term is going to be 11. Graph the first 5 terms. So on my little graph here, we're at, let's go. First term is at 3. Second term is at 5. Third term is at 7. Fourth term, so I'm just going up by 2. So you should see here, this is a terrible graph, but it's going to form a line. Going up by 2, it's got a slope of 2. And 4, write a rule for the nth term. So if this is the first term, second term, third term, fourth term, the rule I'm seeing, a sub n is 2 times n plus 1. So for the first term, I plug in a 1, I double it, I get 2, and I add 1, and I'm at 3. For the third term, plug in a 3, so I double it, I get 6, and I add 1. So if you look, if you double the numbers that I wrote down here, the number of the term, the listing of the term, if you double that and add 1, you end up where you're supposed to be, right? This would be the 5th term, double it and add 1. The 12th term, if I doubled it and add 1, this 12th term should be 25. And if you keep adding 2, eventually we'd get to 25, 7 more terms down the road. Okay, so let's do the same thing over here. 1, describe the pattern. Well, it starts at 3, it goes up by 5, then it goes up by 7, then it goes up by 9. So the amount it's going up is also increasing, so it's probably not going to be a straight line. I'm noticing that these are very close to the perfect squares. 4, 9, 16, 25. See how they're all just 1 less? So the next term I think is going to be, well, the next perfect square would be 36. Subtract 1. I think the next one's going to be 35. Graph the first 5 terms. Let's see if I can do a better graph this time. Not really. 1, 2, 3, 4, 5. So these are 1 through 5. First one's at 3. Next one's at 4, 5, 6, 7, 8. The third one's at 15, so that's going to be double that 8, right? Minus 1. It's like right there. And then the fourth one's way up at 35. That's not, or 24. That's not even going to fit. So this guy is curving and speeding up. So it's kind of like a parabola almost. Write a rule. So here's what I'm thinking for the rule. A sub n is equal to, if this is the first term, it's more like 2 got squared, right? So n plus 1 would give me 2. Square it gets me 4, and subtract 1 to get back to 3. So test that. Once you come up with a rule that you think works, test it by checking some of the other ones. So let's check the second term. I plug in a 2. 2 plus 1 is 3. 3 squared is 9. 9 minus 1 is 8. It works. Try it with the fourth one. 4 plus 1 is 5. 5 squared is 25. Subtract 1, 24. Hey, it works. Okay, so there's our rule. When we add the terms of a sequence together, we end up with what's called a series. So a sequence is 2, 4, 6, 8. right? Just the list. But if I add all of those together, now it becomes a series. That's the difference between a sequence and a series. A series has all the terms added together, and a sequence is just a list. Again, series can be finite or infinite. Finite means it stops. Infinite means it goes forever. When we write series, because they're sums, we use what's called summation notation. We use this Greek letter sigma to represent the sum of something. That's what this big backwards looking E is, or strange looking E, is a sigma. It's a Greek letter. And we use it to demonstrate that we're talking about a sum. So for this finite series, big sigma tells me that I'm using a sum. It's the sum of, here's the rule, 2i, right? It's the first term, second term, third term, fourth term. We're just doubling them. So it's just 2 times the index, the position, starting at 1 and going until 4, meaning there are 4 terms. We start at 1, plug in a 1, I get 2. Plug in a 2, I get 4. Plug in a 3, I get 6. Plug in a 4, I get 8. And then I stop because I stop at 4. And then just to add all those up, right? So the sum of those would be 6, 12, 20, if I just add those up. For the infinite series, it becomes a little bit more difficult because it doesn't stop. It goes forever. So we write it the same way, but instead of stopping at 4, we're going to put an infinite symbol up there to demonstrate that this goes on forever. Okay, so let me draw one of these real quick just to kind of show you the general pattern. That's not great, but you know what to do. So you put the rule over here. This is the I represents index, so this would be the starting value. And this would be the ending value. Right, so this has to be a rule in terms of I, and this will be an I equals to tell you where you start, and this will be the end of I. You don't usually write I equals at the top, you'll just put the number, but it's the maximum value for I. Okay, so let's practice a little bit. Write each series using summation notation. The first thing we have to do is come up with a rule. So we're 25, then 50, then 75, probably going to 100, so we're going up by 25. This is the first, second, third term, right? So if I took I, meaning the index 1, 2, and 3, and I multiplied it by 25, 25 times 1, 25 times 2, 25 times 3, it goes on forever, right? So I want the sum. I'm going to start when I is a 1. That'll give me 25. We need to figure out when I stop. So if I were to divide that by 25, what are we going to get? What do I have to multiply 25 by to get 250? Well, that'd have to be 10. So this represents the series of 25 times I when I starts at 1 and goes to 10. So it's going to be 10 terms. This represents the sum of all of those if I added them all up. I don't know what that is yet, but that's what that shows. Okay, this one's a little bit tougher. Let's come up with a rule. Remember, this is the first term, second term, third term, fourth term. I'm noticing that these numbers, the numerators, represent the index, right? So if we just took the index, or I, and divided it by I plus 1, wouldn't that represent each of these fractions? 1 over 1 plus 1, 2 over 2 plus 1, 3 over 3 plus 1, and 4 over 4 plus 1 will show me those. So that's my rule. These are really hard to draw on this tablet. Hopefully your sigmas will look a little bit better than mine. I is going to start at 1. Plug in a 1, I get 1 over 2, which is what I want. Now, this ellipsis over here means it goes on forever. So we're not going to have an ending value. We're going to put an infinity symbol. So from 1 till forever, add up all the terms that are created by taking 1 over 1 plus 1, and then 2 over 2 plus 1, and then 3 over 3 plus 1, all the way until forever. And that represents the total. I don't know what that is yet, but that's what we're looking for. Okay, so here's a yo-yo. Pause this for 2 minutes, and give this a shot, and then come back. Okay, so we need to write this using summation notation. So again, we have to find a rule first. 5, 10, 15, etc. Looks like we're going up by 5. Those are easy ones because that's just going to be 5 times the index. Right? If this is a 1 and a 2 and a 3, multiply those by 5, I get 5, 10, and 15. It works just fine. So I need my sigma. I is going to start at 1. That gives me 5. What does it go to? Well, just divide that by 5. We'll get 20, which means I need 20 terms. Over here, a little bit tougher again. I'm always looking for a pattern to represent the index compared to each term. So I see a 1, there's a 1 on top, and then there's a 1 plus 1. I could see maybe using that rule we had on the last page. But then I jump here and it doesn't work. What do you notice about these tops in the numerators? 1, 4, 9, 16. Those sound like perfect squares to me. So if I were to do I squared, that would be 1 squared, 2 squared, 3 squared, 4 squared. That'll work. Now how do I compare the bottom? Well, that's the I plus 1. Here's I squared plus 1, I squared plus 1. So I want the same thing that's in the top, but I want to add 1 to it. So there's my rule. And this is the only way to figure this out, guys. It's just kind of like play around with it and look for the pattern. There's no secret formula or recipe. It's just a little bit of logic to figure out how are these being constructed? What pattern can I find? I find it's very helpful to start with these, the index numbers, like the first term, second term, third term, and try and build it from that, because those are the values we need to write the rule from. This will start when I is 1, and when does it go till? Well, there's no stopping point, so this will go till forever. Man, that's not good. It's a little better. Okay. Now, finding the sum's a little bit different story. So now I want to find the actual value. So here's the rule, 3 plus k squared. We're going to start when k is 4, and we're going to stop when k is 8. So we kind of just need to figure out what those values are. So we need when k is 4, 5, 6, 7, and 8. We're basically just going to make a table of these. So when k is 4, that's 16. When I square it, plus 3 is 19. Then 5 squared is 25, plus 3 is 28. 6 squared is 36, plus 3, 39. 7 squared is 49, plus 3 is 52. 8 squared is 64, plus 3 is 67. So now I just add all those up. So I'm literally going to grab my calculator and do 19 plus 28 plus 39 plus 52 plus 67. When we add all those up, we get, or I get, 205. So the sum of this series from the 4th to the 8th terms is 205. There are some special series that come up, and here are 3 of them. So if I want the first n terms of 1, this sounds way more complicated than it is. Let's look at the rule. The rule is 1. Start when I is 1, go till it's n. So what I'm really doing is this is 1 plus 1 plus 1 plus 1 plus 1 forever. So if I have 72 ones, what do you think my total is going to be? 72. So these two numbers will always match if our series is just 1 plus 1 plus 1 forever. Now that's super basic, but it is a series that happens. How about the sum of the first positive integers, first n, so however many this is. Now this is a little bit different. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. That's a little bit more. So the rule for that is whatever this n is, n times n plus 1 divided by 2. We're basically just kind of finding an average in a sense, but not exactly. Right? We're trying to use the final term, multiply it by the next term, and divide by 2. So if I want the first 12 positive integers, that's 12 times 13 over 2. So I could divide these out. It would be 6 times 13, or 78. So if you add up the first 12 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, if you add all those up, you get 78. Or if we square those, some of the squares of the first positive integers. So if the rule is I squared, 1 plus 4 plus 9 plus 16, here's how we do that. If you want the first 5 of them, so 5 times 6 times 10 plus 1 is 11. So 5 times 6 times 11, or 5 times 66 divided by 6. I can cancel those out. 5 times 11, you're going to get 55. So if you add up 1 plus 4 plus 9 plus 16 plus 25, you get 55. And you can check that by just plugging these in. It's a much faster way if we know these rules. Now, finding these rules can be tough, and that's what makes sequences and series an interesting thing in mathematics. So go ahead and pause this if you need to write these 3 formulas down. Label them carefully so you know what they're for, and then jump down here and find the sum. You might be able to use those formulas. You might not. So go ahead and pause this for 5 minutes, however long it takes, and then come back and I'll do these 4 for you. Okay, let's look at this first one, number 13. We're doing 8 times the index from 1 to 5. So let's look back here. Do we have anything like that? No. I've got 1, the index, or index squared, but nothing times an index. So we're just going to have to figure them out. So the terms are, the first one, 8. 2 times 8 is 16. 3 times 8 is 24. 32, plus 40. And we got 5 terms there. 1, 2, 3, 4, 5. So we just got to add those up. 8 plus 16 plus 24. 8 plus 16 plus 24 plus 32 plus 40. I get 120. Now there is a shortcut we could use. If you look back to this one, if we use this formula and then multiply by 8 when we're done, we'd get the same thing. So n times n plus 1 divided by 2. So if we jump back over here, if we did n, which is this guy, 5 times 5 plus 1 divided by 2, but then I have to multiply by 8 because that part's not there, so I multiply that by 8, right? Now let's just simplify. 2 goes into 8 4 times, so that's 5 times 6 times 4, really. 5 times 6 is 30, times 4 is the same 120 we got before. So you can kind of adjust these formulas if you notice the patterns. 15. The rule is just 1, so we're just adding ones a whole bunch of times, right? 34 times to be exact. So if you add up 34 ones, what's your sum going to be? It's got to be 34. Over here to 14. Let's jump to 16. 16. K from 1 to 6. Now that is one of the formulas we had, right? We just used it. If formula is just the rule, notice it doesn't always have to be an I. Like this one's using K's. These two are using I's. Whatever this variable is what the variable in the rule should be. It could be X, it can be N, it can be I, it can be K, whatever. But this number needs to match up here. So let's jump back. If we're using just the value from 1 to whatever, it's just that whatever times the next one divided by 2. So I want 6. So I'm going to do 6 times 6 plus 1 over 2. So really that's 6 times 7 over 2. Well, 2 goes into 6 3 times, so it's just 3 times 7, which is 21. So if I add up 1 plus 2 plus 3 plus 4 plus 5 plus 6, we get 21. And then last, but k squared minus 1 from 3 to 7. That one is definitely not a rule that we have. So we're going to have to just do it. So I need the third term, fourth term, fifth term, sixth term, and seventh term. There's not 1,000 of them. Now, if this went all the way up to 1,000, this would be a much more difficult problem. 3 squared is 9 minus 1 is 8. Plus 4 squared is 16 minus 1 is 15. 25 minus 1 is 24. I'm squaring these numbers, right? 36 minus 1, 35. 49 minus 1, 48. And then I'm just going to add those up. 8 plus 15 plus 24 plus 35 plus 48. I'm coming up with 130. Okay, so take a second, make sure that makes sense. All right, you are on to the homework. Good luck.